See a picture up on the board right now. Joshua said he thought it was a model of an atom. It is. What is it that's in the middle of that atom? Yeah, Hamish? Yeah, it's the nucleus, and inside the nucleus are protons and neutrons. The protons are positively charged, right? And the neutrons are not negative. The neutrons are neutral, right? Neutrons are neutral. And those protons and neutrons are pretty tightly bound together in the nucleus by this force that we call the strong nuclear force. That's not important for you right now. Later on in the year, that force called the strong nuclear force will be important to you. Anyways, they're pretty tightly bound in this small area of the atom that we call the nucleus. The rest of the atom, most of it is empty space, but there are these tiny little negatively charged things orbiting around the nucleus, and these tiny little negatively things are called electrons. Good. We're studying electricity in this unit, and as we study electricity, it is based primarily on the electrons that orbit around this nucleus. These negatively charged, almost massless things that orbit around the nucleus. If we talk about objects as opposed to individual charges, then those objects can have one of three different charges. They can be positively charged or negatively charged or neutral. If I take a balloon and just hold it in front of me, it's going to be neutral. But if I rub that balloon against my hair, then the balloon becomes negatively charged. My hair, by the way, at the same time, becomes positively charged. As the balloon becomes negatively charged and my hair becomes positively charged, it's because of a movement of charge from one to the other between my hair and the balloon. The one that becomes positively charged, my hair, actually loses electrons and becomes positive. Ultimately, it's positive because it has more protons than electrons. It didn't to start off, but as I rubbed it against the balloon, it lost electrons, didn't gain any protons, just lost electrons, and therefore became more protons than electrons. The balloon that has a negative charge after I rub it against my hair has a negative charge because it gained electrons. It has more electrons than protons. We're not suggesting here that a negatively charged object has just electrons. It has to have protons. Protons are in atoms. The balloon becomes negatively charged. It doesn't mean that there are no atoms in the balloon anymore. There are no protons in the balloon. There's just as many as there were before. But now you have excess electrons. So you end up having more electrons than protons. By the way, if it's neutral, which is exactly what it was before I rubbed it against my hair, it's an equal number of protons and electrons, which is the normal state for things, right? If an atom has 6 protons, normally it has 6 electrons. Until you do something to it to change that. How do we measure the amount of charge that something has? We rub that balloon against my hair, it becomes negatively charged. Well, how much negative charge? Clearly, if I rub it twice against my hair, it's going to gain a certain amount of charge. If I rub it 10 times, it's going to gain more charge. How do we measure the amount of charge? Well, we have to have a unit for the amount of charge. Just like we have a unit for speed and for acceleration and for momentum and for energy. The unit for speed is meters per second. The unit for energy is joules. The unit for electric charge would be the coulomb. We abbreviate that with a C. The symbol, by the way, is Q. So we'd say for speed, V is equal to 10 meters per second. This would be the symbol. This would be the unit. For charge, we'd say 10 coulombs. This would be the symbol. This would be the unit. Now, just so you know, a coulomb is a really, really big unit of charge. You don't really have any concept, though, internal concept, as to how much a coulomb really is. Like if I tell you a car is moving at 10 meters per second, you can kind of visualize how fast that's moving. If I said a person has a mass of 50 kilograms, you have some internal notion of what 50 kilograms is, right? But if I said a balloon has a charge of 5.5 times 10 to the negative 9 coulombs, you would have no internal notion of how much charge that really is. A coulomb is a really, really big unit of charge. If you've got a coulomb of charge, you've got a lot of charge. I'm going to put that in perspective here right now. The charge of an electron, which by the way is the same magnitude as the charge of a proton, but opposite sign, an electron is negative, a proton is positive. They're both 1.60 times 10 to the negative 19 coulombs. That's a small amount of charge. Okay, that's a small amount of charge. That means that it takes a whole lot of electrons and protons to give you a coulomb of charge. In fact, it takes about this many electrons to make a coulomb of charge. About 10 to the 19 electrons to make a coulomb of charge. That gives you a bit, I think, better idea as to how much a coulomb of charge really is. It's a big unit of charge. It takes 10 to the 19 electrons or 10 to the 19 protons to make a full coulomb of charge. The reality is, because it's such a big unit of charge, most of the questions that we do in this unit involving charge will not be in coulombs. Most of them will be in nano coulombs or micro coulombs, and you'll have to do the conversion to coulombs. Okay, be aware of that. Okay, last unit, sometimes we got kilometers per hour, we had to convert to meters per second, but we often got meters per second. Okay, this time around, we're gonna mostly get units other than the standard unit. Almost every time we see a question, we're gonna have to do that conversion back to coulombs. And as we see that, I'll show you exactly how to do that conversion. This is the first page of your data sheet. You can open up your data sheet if you want, or you can just refer to the page on the board here. I don't expect you to remember what the charge of an electron is, although I would suggest to you by the end of the year, you probably will remember it because we'll use it enough times. You don't have to, though. It's on your data sheet. Where are we going to find the charge of an electron on my data sheet? Yeah, Joshua, where do you see it?
I see it right there. Charge
Okay, top right-hand corner under particles. If we scroll down here, we see an electron has a charge of negative 1e. That doesn't tell me that it's negative 1.6 times 10 to the minus 19, no. So where do I get that from? Well, let me tell you that an E stands for an elementary charge. And right now, you don't know what that means. Later on this year, I'll explain to you what an elementary charge is. For now, just trust me. Okay, just trust me on this. An elementary charge is 1.6 times 10 to the minus 19 coulombs. So if you've got negative 1e, then you've got negative 1 times 1.6 times 10 to the minus 19, or negative 1.6 times 10 to the minus 19 coulombs. If you've got plus 1e, like for a proton, then it would be positive 1.6 times 10 to the minus 19 coulombs. An alpha particle? You're not even going to learn what an alpha particle is until unit 4, our last unit here. You're not going to learn what it is until unit 4, our last unit. But we know that it has a charge of 3.2 times 10 to the minus 19 coulombs because it's plus 2 times the elementary charge. All right? Okay, be familiar with where to find the charge of these things. Okay, not only right here, but you've also got to refer over here to the elementary charge as well. Somebody's going to ask me on your next unit test, on your first quiz even, somebody's going to ask me, oh, what's the charge of an electron? I can't remember. And my answer is going to be, check your data sheet. Okay, check your data sheet. But you need to know where to find it on your data sheet. It's a little bit trickier than some of these things are. All right. These are ions. You guys know what an ion is? If you take chemistry, you know what an ion is, right? William, what's an ion? Oh, I thought I saw your head kind of nodding there. What's an ion? Yep, Matt. Yeah, it's an atom that's charged, right? It's either gained electrons or lost electrons. It's become charged. This is an aluminum ion. It says 3 plus, whatever that means. Na sodium ion that has a charge of plus. Oxygen 2 minus. These are ions that have charges of either plus or minus because we've either gained or lost electrons here. Aluminum is 3 plus. That means the charge of aluminum is 3 times the elementary charge, which is 3 times 1.6 times 10 to the minus 19 coulombs, which is 4.8 times 10 to the minus 19 coulombs. I just want you to be able to recognize when you see an ion like this, what its charge is. Okay? It's just a notation thing. We just have to know that we multiply the elementary charge by 3 there. For sodium plus, we'd say the charge is 1 times the elementary charge, or just 1.6 times 10 to the minus 19 coulombs. For oxygen 2 minus, we would say it's negative 2e, negative 2 times the elementary charge, or negative 3.2 times 10 to the minus 19 coulombs. I want to take a look at a quick example here now that's on the example handout that I gave you at the beginning of class here. It says a balloon is rubbed against hair, gaining a charge of negative 9.6 times 10 to the negative 9 coulombs. Determine how many electrons the balloon has gained or lost. How many electrons has the balloon gained or lost? Well, first of all, I want you to recognize that it is the electrons that are moving. Can anybody tell me why, as a little aside here, maybe why it's electrons that do the moving? Why is it electrons gained or lost versus protons gained or lost? Yep. Good. Perfect answer. The protons and neutrons are in the nucleus, and there's what we call a strong nuclear force in the nucleus that keeps them together. You'll learn more about that in our last unit as well. But that strong nuclear force is too strong under normal circumstances to allow those protons to go anywhere. There is an electric force that keeps the electrons in orbit around the nucleus, but it's a much weaker force. So it's a lot easier to break the bonds of that force and allow the electrons to move somewhere than it is to break the bonds inside the nucleus and allow those protons to go somewhere. Think about this, okay? Think about this. If you move a proton from one atom to another, then you've changed the atom into something else. It's not carbon anymore, it's nitrogen. It's not uranium, it's thorium. You've just caused a nuclear reaction. When you rub a balloon against your hair, you do not cause a nuclear reaction. Okay, it's only electrons that are doing the moving. So in this question, has the balloon gained or has it lost electrons? Well, because it became negative 9.6, we know that it must have gained negatives. It's gained electrons. If it became positive, it doesn't mean it's gained protons, it means it's lost electrons. Now, how many is it gained or lost? Yeah? 6? No, but you're on the right track there, I think. Let me give you an analogy to maybe help you to work through this. Let's say tonight you go down to Safeway and somebody told you the oranges at Safeway are really good right now. So you decide you want to go buy a few oranges, maybe some oranges for your lunch over the next couple of days. And you look at an orange and you're like, this is a good looking orange. Looks really juicy. You weigh it and it weighs 200 grams. Okay, remember that orange weighs 200 grams. And then you see this, you see this paper bag over there with some oranges in it. You're like, okay, that works. I'll buy that paper bag full of oranges. You take it to the counter, and the cashier weighs the bag of oranges 600 grams. You never did count how many oranges you have in the bag. How many oranges do you have in the bag now, though? One orange is 200 grams. The bag of oranges that you just bought has 600 grams. How many oranges do you got in that bag? This isn't rocket science. 3, right? How'd you figure that out? 600 grams divided by 200 grams is 3. We took the total mass and we divided it by the mass, the total mass divided by the mass of one orange, right? Intuitively, even though not very many of you answered that question, we all knew that, right? We all knew there was 3 oranges in that bag. It's a little bit harder when you're dealing with charges of electrons and so on, but we go about it in the same way. If the total mass divided by the mass of 1 gives you the number of oranges, then the total charge divided by the charge of 1 electron will give you the number of electrons. The total charge here is negative 9.6 times 10 to the negative 9 coulombs. The charge for one electron from your data sheet is negative 1.6 times 10 to the minus 19 coulombs. And when you do the math there, you end up getting 6 times 10 to the 10. 6 times 10 to the 10 electrons. Okay, that's a little bit harder to kind of work through, but it's the same thing as the orange analogy, right? It's a total divided by the amount for one. Remember that, because you're going to have to do that several times this year, find the number of the electrons. Beyond, though, remembering it's a total charge divided by the charge of one, okay, remember the reasoning we used. When you want to find a number, whether it's oranges or electrons or photons or anything else, a number of something is always going to be found by taking the total something divided by the amount for one. So it might be total mass divided by the mass of one, the total charge over the charge of one, might be the total momentum over the momentum of one, might be the total energy divided by the energy for one, total something divided by the amount for one. Yes, you were. Yeah, so close, but only off by a factor of 10 to the 10. So not bad. You had the base. You had the right idea. Absolutely. Yep. Yeah, absolutely. Is that okay? All right. There's our diagram of the atom again. Yeah. We got protons in the middle, neutrons, the electrons orbiting around. We just answered this a few minutes ago. Movement. What moves? If something's going to move from one thing to another, from the hair to the balloon, it's going to be the electrons, yeah. And it's going to be the electrons because they're not as, the force keeping them in place isn't as strong. It is possible under certain circumstances to break the force that acts between the protons and the neutrons as well, but not under normal circumstances. Certainly not by rubbing a balloon against your hair. You're not going to cause protons to move anywhere. Couple more terms now. Difference between a conductor and an insulator. You guys know what a conductor is? At some level, you probably do, right? What's a conductor? In the context of electricity, not heat or not trains. What's a conductor, Hannah? Yeah, it allows for the transfer of electricity. In other words, it allows for the transfer of electrons because that's what actually moves, right, is the electrons. Now, why does it do that? It does that because the electrons in the outermost levels of a conductor aren't so tightly bound to the nucleus. They're free to move, or relatively at least free to move. A conductor is a material that has those properties. An insulator, on the other hand, has the opposite properties. An insulator has has electrons that are too tightly bound to the nucleus to move around very well. We're not suggesting that an insulator can't have the electrons moving from one to another. It's just a lot harder. Some materials are hospitable to electrons moving, some aren't. Conductors are, insulators are not. You don't have to copy this down. This is just a chart that describes for us similarities and differences between certain materials. You can see up at the top here we have what we would call conductors. But there's varying degrees of conductivity. We go from about 10 to the 3 to 10 to the 8. That's not, there's no units associated with that. It's relative conductivity. 10 to the 8 is just 10 to the 5 times the amount of conductivity of 10 to the 3. If you've got something that's 10 to the 7 and you got something that's 10 to the 6, well, 10 to the 7 is 10 times better of a conductor than 10 to the 6 is. Take a look down here. These are the insulators. You can see that the conductivity of the insulators is much, much lower, 10 to the minus 10, 10 to the minus 12. It doesn't mean that they can't conduct. They can, just not nearly as well as the conductors. If we look at one of the poorest one of the poorest conductors, which is rubber, it's about 10 to the minus 15. Silver, which is one of the best conductors, is 10 to the 8. That means that they'll both conduct, both of them will, but silver will conduct 10 to the 23 times better than rubber will. Yeah, rubber's a worse conductor than wood, so it's a better insulator than wood. So if you get struck by lightning, what do you want the soles of your shoes to be made out of? Silver or rubber? You know what? It doesn't really matter. I'll be honest with you. It doesn't really matter because they both conduct electricity. Silver conducts way better. It just maybe might end it quicker for you. That's all. But if you're wearing rubber soles, listen, you got several million volts of potential difference when you're talking about lightning. Okay? If you're wearing rubber sole shoes, even though it doesn't conduct nearly as well as silver does, it's still going to conduct that electricity through, and you're still going to get electrocuted. Okay. Under less extreme circumstances, we would use rubber to insulate us from electricity, okay? Or plastic or wood. Yep, go ahead. Hey, what do all these conductors seem to have in common? They are all what? Yeah, I see. They're all what? Rachel? Look at them. Silver, copper, aluminum, iron. They're all objects that are made out of? Yeah, they're all metal objects, right? Metal tends to be a good conductor. And if you've taken chemistry, you know that the electrons on the outer levels of metals aren't as tightly bound to the nucleus. So no, mercury at room temperature is actually a liquid. Yeah, yeah. It would have to be, I'm not sure what the temperature it would be to freeze, but at room temperature, it's a liquid. And it does conduct. A thermostat at home, most people have digital thermostats now, but I'm not sure exactly the inside mechanism of those. I haven't looked in one, but the older ones, where you push the little dial over, you know what I mean? Push that little switch over for the thermostats. What that did is change the balance of a little glass tube of liquid mercury, and then when it slid down, it would complete an electric circuit. So liquid mercury would actually complete the electric circuit, which would allow the furnace to turn on. Okay? So it's liquid at room temperature, and it is a pretty good conductor. Not as good as silver or copper or aluminum, but still a pretty good conductor. Versus an insulator, what do those all have in common? They are all non-metal objects. Right. Right. Thank you, Rachel. Non-metal objects, wood, glass, rubber. And you can see that they still conduct, just not nearly as well as conductors do. That's all. All right. 3 laws of electric charge. We'll talk about these, and then we're going to call it a day as far as this new stuff goes. Maybe. The first law of the electric charge, well, it's kind of like the first law of, I don't know if I call it the first law of humanity, but one of the laws of humanity. Sometimes people that are alike just don't get along. Sometimes if you want to get along with somebody, they have to be different. Opposite charges attract. And like charges repel. So positive attracts negative, negative attracts positive, but yet positive repels positive and negative repels negative. They push each other apart. If you start dating somebody that's too much alike, sometimes you just don't get along. You need a little bit of difference. You need to be a little bit opposite to attract. Finally, our last one. Charged objects will attract neutral objects. This word objects is important here, and you'll see why tomorrow. For now, just trust me. Protons do not attract neutrons, not electrically anyways. There is a force of attraction between them. We alluded to that earlier. It's called the strong nuclear force. But there's no electrical force of attraction between protons and neutrons. But yet one's positive, one's neutral. Positive does not attract neutral. Negative does not attract neutral. Positive objects attract neutral objects. A balloon that is negative will attract a wall that is neutral. But they have to be objects. And again, tomorrow you'll see why that's the case.